energy. Well, if we have the Q curve, which is, as I said, the most important information on nonlinear capacitors, if we have the Q curve, we can locate the energy stored in it. And as it turns out, this here is the area. The area here is the energy stored in the capacitor. This is this integral. Now, VDQ. Now, in a linear capacitor, this is a straight line, and you can find out that it comes up to be CV squared over 2, which obviously will be larger than this area here, because it's going to be a straight line, and this will be, again, the area, but it will be half a triangle, that triangle here, which is larger, okay? So this makes sense, because as the slope is going down, capacitance is going down, you can, for the same delta V, you can inject less charge, so therefore less energy into the capacitor, and therefore the total energy here becomes smaller and smaller. And you can either do this integral, or you can take the area and subtract this integral, which sometimes is easier to do, which is Q dV, okay? So because this is the y axis. Now, again, in SPICE, we can very easily get this area. I'll not go over it in details. Excuse me, because I'm afraid that I may not finish all the slides. And again, I can generate back the derivative, take the integral of the derivative gives me the Q curve, and then I'm doing this area. This is this area, this first part here, and this is the rest of it, and here is the energy. And here we see a picture. I have started with the derivative or local capacitance, digitized it, put it into the table here, and then generated with SPICE this, let's say, I reconstructed this is reconstructed, and then this is the Q curve, which is the integral of this, and then energy stored, I have it here. Now, obviously, again, I'll skip this a little bit. If you take just the derivative or local capacitance and assume that this is the capacitance, meaning that this is your curve, then obviously you get the wrong number, because then you get this area, which is much, much smaller than this area. That is, if you just assume that the final capacitance or the derivative of the final capacitance is the representing the whole story, then obviously this is incorrect. Okay. Now, I'll do an exercise, and that is, I'll take a linear capacitor and charge a nonlinear capacitor. Okay? This is the linear capacitor. The QV curve is a straight line. This is the nonlinear capacitor. I'm assuming that this one has voltage V whatever L, linear, and this one has, okay. So here is a linear capacitor, this is a nonlinear capacitor, and I'm connecting the two. What happens? Well, you can do it analytically if you approximate this to a sort of some function, but it's nice to do it sort of to understand it in a graphical way. And I'm doing here what used to be done with the so-called load line. I don't know how many of you are familiar with the load line of a transistor. You take the transistor, then you flip the resistor, and then you say that the sum of voltages is this power supply. So I'm doing the same thing. The sum of the charges, which is the conservative parameter here, is the same. Not changing when you connect the two. You have the same charge. Charge is not disappearing or creating. And the cross point will be the voltage. This is the initial one for this one. This is the initial one for this one. The sum is the same. And this will be the voltage of the two. This is the charge now on the linear capacitor. This is charge now on the nonlinear capacitor. And this is, by the way, this area here is the energy lost. So you can tell how much energy is lost in this process. The energy lost is small because the two voltages are close. I just took this example. Okay, now one more point, and that is hysteresis. Now, we associate the hysteresis with the losses. The area is energy, and the number of times that we circulate the area, that is the frequency, will be the power. So energy, the area, times frequency is the power. This is why in the equation we had before, frequency was multiplying the part of the hysteresis, which was V squared. Now, however, one has to bear in mind that if you take just a capacitor plus a resistor, no hysteresis, and you plot, again, this will be the charge as a function of voltage, you'll get an ellipse because there is a phase shift here. So what I'm saying is that one has to be very careful because the resistance of parasitic resistance of interconnection, etc., of the capacitor may also introduce a phenomena that looks like a hysteresis, while they are not really the hysteresis, but this phase shift. So this is just an observation, not very important. So I'm going now back to the AC signal, large signal. This is really very poorly described. I have shown you earlier that you can get this information by first getting the Q curve from preferably the local capacitance, because you have the local capacitance over a wide voltage range, and then you can take the slopes at different points and get the CAC, as I called it. Some vendors do give this information. It's very seldom. For example, here, this is from CDE, and here what we see. Let's start, well, basically, these are for two different dielectric materials, X7R and Z5U. What we see here is large signal excitation now. This is the real thing. And we see capacitance change. This is with capacitance change with no AC, just DC. Now here they mean actually the local capacitance, okay? This is a logarithmic scale, so it looks a little bit different from the curves we've seen before, which were linear, and these are logarithmic scale. But what I'm interested is in this part, and what you can see that there is a increase in capacitance. Now this increase we talked about, this is the very beginning, okay? Here's up to 10 volts. And then it goes up. Now, this means that this was measured with a signal which is like 60 volts or something like that, and looking at the actual equivalent capacitance, that is current and voltage and the ratio between them for the given frequency. Notice that we have also here the dissipation factor, which is ESR, say, and also it's sort of going up, and this is because of the very large swing that we have in this AC capacitance. So as I've said, only few vendors give this information, but you can reconstruct it the way I've shown it. Another company that gives this information is Johnson Dielectric. And here it is. Again, we see the capacitance change as a function of AC excitation. Again, this will be very important for resonant converters because you have large excitation and you like to know what is the equivalent capacitance for the large excitation. And this is now under different DC voltages, okay? And this is the curve that they have generated. As I've said, we can generate it ourselves from the information that vendors are giving by constructing or reconstructing the Q curve, and then you can do everything. You can get all this information without any problem. Okay, now I'm moving to simulation. Now, in some cases, you'd like to do a simulation. This could be also for a PWM converter with a output capacitor, or you can do it for definitely for a resonant converter to find out what is the equivalent capacitance that you have without going into the old graphs and calculations and approximation, doing it by simulation. For that, you need a model, simulation model of a nonlinear capacitor or voltage-dependent capacitor. That's what you need. So again, the key is first of all to understand what we are talking about. Which capacitor? Which model of capacitor? Is it the derivative? Is it the total? Okay? And maybe you will not be surprised, or I was surprised to find out that in many papers and data sheets and short articles, people were confused and did not use the correct definition of capacitance or values of capacitance, and therefore they did simulation, but the results are incorrect because they were using the incorrect capacitance. So the way to do it is first of all to decide which capacitance are we going to use in the simulation. Is it the derivative or is it the total? AC is a little bit complex, so the two neat ones are either the derivative, that is the local one, and we have the curve very nicely of how this local capacitance is changing with voltage, or the total, which is basically also can be obtained from the Q curve, or it's CAC with zero bias, okay? So there are many, many ways to do it, and let's go over them fairly quickly. Suppose we start with the definition of total. What is total? Total is at a given point. Let me go here. We are talking about the ratio between the Q and V. This slope is the total capacitance. So this is one definition. Here is the definition. From here we get the state space equation, from which we understand that in order to simulate a capacitor using C sub t, total capacitance, I need to generate a current according to this equation. That's what I have to do. That is, I need a current source with this features. G value in PSpice is a current source. It depends on an expression that you write. This is the current source, and I'm labeling this C3 and C4. This is the capacitor that I'm emulating. These 2 points are the capacitor, and they go into this current source. Now the current source has to follow this equation. Very easy. What does it say? It says the total capacitance times the derivative times of the voltage, voltage times the derivative capacitance. So the first thing I do, I generate a voltage which represent for any given voltage here, represent a capacitance. I could have done it with a table, and this is what I done, and I sort of approximated the straight line. So I have 2 points on the table, like here it is, this point, and I approximated the straight line. So you have 2 points, the beginning and the end. This is the table. The table is fed with the voltage. This is the voltage between these 2 points, the capacitor voltage. And here we get a voltage which any given time, depending on the voltage here, represent the capacitance, the total capacitance. And now I'm writing an equation in the syntax of PSpice as follows. Voltage of this is CT, the voltage of this, times this is a operator in PSpice derivative. Derivative of what? Of the voltage here. This is the voltage here, derivative of the voltage, plus the voltage here, voltage of the capacitor, times the derivative of the capacitance. That's it. Okay? Now, these 2 points behave as a voltage-dependent capacitor for DC, AC, transient, everything. This is the approximation that I did, and I did it 2 ways, one with 2 points, and one I approximated to the linear curve. This is a linear curve, okay, which I'll use later on instead of the table, okay? Another way is to use the equation, as I've said, instead of table. Let's skip this one, it's not that important. Another way of doing it is to start with this equation, but rather than to look at the current, to look at the voltage or find an expression for the voltage. This I can do by taking the integral of the 2 sides, which shows that the voltage on the capacitor is the integral of the current divided by CT. The voltage is here. CT I've approximated by this equation. So I take now another operator which is called SDT, which is a integrator, integrating the current that goes in here. This is the current of the capacitor, and dividing it by CT, which is approximated by this equation. So this is another way to do it. I have other options, and the interest of time, I'm not going through all of them. I'll just pick up one more, which is representative of some of them. And this one is different from what we have said before in 2 respects. One is that I'm using C sub D, that is the local capacitance, as the parameters I'm working with. And secondly, that I'm doing actually the state space equation by cloning. What does it mean? I'm taking a linear capacitor, I see how it behaves, and then I modify the behavior by the fact that CD is changing. Okay? So here I have, again, terminals of a capacitor. They are fed to this E value, which produces, I'm sorry, I'm sorry. Something is wrong here. This should be flipped over. I'm sorry. Okay? This should be flipped over, the input and output. Please do this. Should be flipped over. Been plotted incorrectly. Okay? So I'm taking the voltage and I'm just duplicating it. And I'm doing it in order not to load this. This is the one-to-one amplifier. Whatever you have in comes out. And now a current is generated in the capacitor. This is a 0.95 microfarad capacitor. I'm measuring this current. A method to measure the current is to put a zero voltage source and then to refer to it. Current of V1. This is V1, the current through it. So I can refer to this current. It's a sensor of a current. So I've imposed the voltage on a linear capacitor, but now I am changing it according to the behavior of the nonlinear capacitor, and this is done by this expression here, which is changing the behavior, multiplying it by the nonlinearity of the capacitor. Okay? So it has the two effects of, number one, cloning, and number two, using C sub D in the definition. The end result is that you can do it any way you wish if it is correct. You can't do it if it is incorrect, because you'll get an incorrect answer. So for the 6 options that I have described here, here are the results, one on top of the other. What we see here is a circuit in which these models were exposed to the same excitation. It was a divider here. And you see the voltage generated is exactly the same thing on all of them. Also, this model is correct for the time domain. I have here a excitation, which is a pulse on which a small AC signal is superimposed, and you see that the output of all these models is exactly the same. They are all one of the other. And here I'm showing the difference in the response of a linear capacitor and a nonlinear capacitor. This is an RC circuit, R and C. The linear capacitor has an, of course, exponential rise. This is similar, but you see that at the beginning they're the same, but as the voltage starts to develop on the capacitor, it's decreasing the capacitance. So it's speeding up the rise time. So this is why this rise time is faster with the nonlinear capacitor than with the linear capacitor. And this is a time domain simulation, and we see that we get the same result with all these models. Okay. And just to verify that the model is really okay, this is another sort of, it's similar to what I've shown before with the table, the model of a capacitor. We expose a real capacitor. We expose it to DC plus an AC excitation. This is a DC blocking capacitor. And did some experiments here with this real capacitor, which we modeled here from the datasheet. In fact, it's not from the datasheet. We measured the capacitor, took the local capacitance with same setup. We actually measured the local capacitance and then built the model for the time domain. This is the reproduction of CD with the model, and then we expose it to a pulse. Okay, this is the pulse, and this is the rising edge, the falling edge, and the straight line is the measurement, and the dots are the simulations. So you see that the simulations are very, very good, and they're reproducing the behavior of the nonlinear capacitor. Okay, let's see where we are. Good. So I think this is the basic information that I conveyed here. Sort of covers the peculiar things about capacitor. Naturally, there are many, many other details, but I think we have here covered the sort of non-conventional parameters or parameters that are less known in ceramic capacitors. What I'm going to do next, as I've said, is to show how we can take a disadvantage of the capacitor, and the disadvantage is that the capacitance is changing with voltage, and turn it into an advantage, to use it, to do something. Now, there have been varactors, as you might know. These are voltage-dependent capacitors. They are they are actually built around a junction, a PN junction, a diode, which is biased, and then you can change the capacitance. But capacitances that you can get are picofarads, and the current that you can pass is milliamps. That's very small. So this is not for power, it's not a power conversion. So some time ago, I decided to look at this possibility of using the nonlinear effect, the voltage dependence of the ceramic capacitor, to build converters in a different way. So the first one that I'm going to show is the series resonant converter. Now, if we look at a resonant circuit like this, we have a resonant element, L sub R and C sub R. This represents the load. So this is a series resonant, and we know that the transfer function between the input and the output is a function that can be expressed in a neat way like this. Q is related to the load, actually the ratio between the characteristic impedance and the load, and F is the switching frequency, or the excitation, I shouldn't say switching, it's the excitation frequency, and F sub 0 is the resonant frequency. So this is classical resonant converter, electrical engineering 101, okay? And of course we have the response here, which is dependent on Q, which is the load. Now notice that the response is a function of the ratio between the frequencies. So we can get a similar response if we change the resonant frequency. Keep the switching frequency constant and change the resonant frequency. How can we do it? We have a capacitor that is changing, so we can change the resonant frequency. Now, what's the advantage of it? First of all, there are many applications. I don't know if you are aware that a variable frequency is not accepted at all. Sometimes because you like to synchronize two parts, like a power factor with a converter, like to synchronize the frequency. You don't want one to go all over the place, because then you would have a beat between the frequencies, and this could be a big disaster. And in other applications, like radar, communication, you don't want to have frequencies that you don't know, you don't recognize them, and you cannot filter them properly. Because if you know the frequency, you can filter it out, and if not, it's moving all over the place, you have a problem. So If I'm keeping the switching frequency constant and I'm changing the resonant frequency, then I can run a series resonant converter with a fixed frequency. Okay? So here it is. We have a variable capacitor, the same circuit, and now the control is by the capacitance. The C is the sort of the reference capacitor, and C sub S is the actual capacitance that I'm using at each given point. This is now the curve. It's similar. It's not exactly, but it's very similar. And obviously, you can get gain by changing the capacitance. Okay, you change the capacitance, you have different gains. This is the gain of this series resonant converter. So how do you implement something like that? Well, here is a typical half-bridge series resonant converter with the inductor and capacitor. Now we can either use one voltage-dependent capacitor, here it is, plus a capacitor which is linear. Why do we need a capacitor here at this point? Because we have DC component and we don't want to impose this DC on this capacitor. So this is actually a DC blocking capacitor. So it could be a linear capacitor or it could be also a voltage dependent capacitor. And I'm injecting here DC. The purpose of this DC is to shift the capacitance. I don't have to, there's no energy involved. I mean, there's only when you move from one point to another, because this point does not consume any power. It is just a little bit of charge that you have to inject into the point in order to move the DC value of the capacitance, and that's it. And then you can rest till the next time you may need to change the capacitance. How you do it? There are two ways. One is to use a large resistor plus a voltage source, or a dedicated driver that I'll show you that have a high output impedance so that you not load or short AC the capacitor. This has to be a high impedance here, not to short the capacitor for AC. And in this case, what you get, very similar to a resonant converter, a series resonant converter. You have this plot, and here's the phase, which is also very, very similar. Of course, here we have a phase reversal, and of course, in this area, you get zero voltage switching, as you know. So it is possible to do that. And here's the performance. What we see here is Q. Q represents the load. This is the load. V is now, in the experimental system, the actual bias voltage that was imposed on the capacitor to change it, to vary it. And these plots are for various voltage gains. Okay? So this is the envelope, you might say, of operation here. This is the resistance range, and this is the gain range from, say, 0.3 to 0.9, the factor of 3, and with a Q, which is also a factor of, say, of 5 or something like that. And this is now the voltage that you have to inject at the midpoint in order to get the operation correctly and to adjust the resonant frequency to what you need in order to get the particular gain. Now, what about LLC, which is very, very, very popular today? You can do the same thing. You can take an LLC converter. Here it is again, a half-bridge converter. These are the two inductors, LL and C. And then you put a resonant capacitor for the regular LLC. Here I'm showing the transformer coupling and a rectifier. Now, as you might know, in order to analyze a circuit like that, what we do, we replace this portion here, by the so-called RAC. You familiar with that? Let me just say a few words if you are not. What it means is the following. This is a nonlinear circuit. The equation that I've shown you, this equation, assume a linear circuit. Assume that there is some resistor, a rectifier, plus a capacitor filter, plus a load is nonlinear. And you cannot do a phasor analysis on it. To do a phasor analysis, like the circuit, you need to have a linear circuit. So that's a technique that is used, and this was developed by Professor Steigerwald from General Electric, he used to work there, is to replace this non-linear circuit, to replace it by a resistor. How do you do it? You look at the power dissipated or consumed by this part, the power, and you calculate a resistor that will consume the same power. So as far as the resonant circuit is concerned, it does know that now it has a resistor rather than this nonlinear circuit. This is also based on the fact that due to the fact that you are close to resonant, the current is sinusoidal. So what really matters here for the power is the first harmonic of the current and the voltage. And so therefore, you don't worry about the higher harmonics or the nonlinearity here. So this technique is then used to convert this part into a linear circuit that you can now analyze. Okay, so now once we have a linear circuit, we can write the transfer function between here and here, okay, and then translate it, if you want, from here to here, because this is just a transformer, a rectifier. We can find the relationship between the DC here and the AC here. It turns out that for the LLC, which I said is very, very popular today, this is the transfer function between the output and the input. Now, again, the transfer function is a function of the ratio between the frequencies. This is the switching frequency, and this is the resonant frequency. And some other parameters like the ratio between the inductors, here is translating into the DC, etc. So here again, rather than changing the switching frequency, I can change the resonant frequency by the same technique. This is a typical transfer function of an LLC, conventional one. Why do we like LLC? Why is it now very, very popular? Because of this area. What we see here is that for different Qs, that is different loads, the gain is about the same, doesn't change much. So you don't have to change much the frequency, the switching frequency. This is why LLC is so favored today. But with the technique that I'm talking about, you don't have to change the frequency at all, because I can put here, instead of the regular capacitor, I can put a voltage-dependent capacitor, this ceramic capacitor, and bias it to get the value that I need in order to regulate the output. Okay? So this will result in something very, very similar, except that now we work with a change in capacitance. Frequency is fixed. And this ends up to be the transfer function as a function of this C, which is the ratio between the actual capacitance and the reference capacitance. Again, we have Q, and this is the reference capacitance. So here are the comparison. The two looks very much the same, except that here the control is by frequency, and here the control is by a changing capacitor. This was tested experimentally, and this is the test circuit, except that in this case we actually use the resistor here, didn't use a rectifier and a transformer. And here you can see the voltage across the capacitor, the nonlinear capacitor. There are two curves here, one top of the other. One is a simulation with one of the models that I've shown you before, and one is the actual measurement. So you see that they very much the same. See the nonlinearity here of the capacitor, by the way. And here I'm showing you a driver that we have for the biasing. As I've said, in order to change the bias on the capacitor, you have to feed current or charge, as a matter of fact, but you don't you can't load it. This is the impedance has to be high. And here in this design, what we have two transistors, and the output is from the collectors. It's a BJT transistor. So this is high impedance, just like a current source. We do have a window here, a hysteresis you might say, such that when you are in the right operating point, none of the transistor is conducting. Only when you need to change the voltage, it'll excite either this one or this one to inject a little bit charge into the midpoint and therefore change the capacitance. So this actually consumes very, very little power at all because there's just a little bit of charge to inject here. And here are the results for the LLC. Again, this is the envelope of simulation here, of operation here. This now is an experiment in which we change the voltage while keeping the output constant. That is, we change actually the gain ratio that we need. Output is constant, looking for output or regulating it for an output voltage, a constant output voltage, while the input is changing and the resistance is changing. Okay? This is a little bit tricky in LLC. You might know that LLC is a little bit sensitive or not so good for gain changes. Here, however, that is, let me just explain here. In an LLC, it is, you normally work here, and to get very high gain, you have to go to very large Qs, and this causes a lot of dissipation and power loss, so this is not an area that you'd like to work with. So LLC is kind of restricted to a fairly constant gain. While here, we have a change of the input voltage. This is actually reflecting the gain. And here is again the bias that we needed in order to change the capacitance to keep the output voltage constant. And here we have a load change of 10-fold between 15 and 150. Okay, so this was done experimentally. And finally, I'm going to show you another application, which I think is very, very of potential use, and this is for wireless power transfer.
Did you license your ID?
No, for several reasons. we've decided not to.
So it may be used.
Yeah, it is public. This particular one is public domain. That's correct. This one we have not patented. Well, there are many reasons for that, but let's not go into it. Okay. Now, again, we have now another application, which I think is of very high potential here for being very useful, and that is a wireless power transfer. Now, what is wireless power transfer? This idea was actually brought up or invented, you might say, by Tesla 100 years ago. This is a picture from Do-It-Yourself magazine from 1921. And it shows how to build at home the wireless power transfers of Tesla. What it has is a transformer, generate of isolation primarily and high voltage here, has a sparker here, a capacitor, and this is the antenna, the transmitting antenna, and this is the receiving antenna. There's a light bulb, and as you turn this thing on, it'll light the bulb. Now, here we have a resonant circuit with the capacitor. Now, obviously, the resonant here is high frequency, and the high frequency is obtained by the sparker, because the spark has a high frequency content. So some of the frequencies are captured in here, and this is transferred to the ingenious Tesla. And this is the basis of wireless power transfer today, for cellular, for cars, for whatever, toothbrush, what we do. Basically, we do have a transmitter, we have a receiver, two antennas, and then we have one way or another, usually a rectifier, because we need DC for various apparatus, various circuitry that we have. But we might have here a converter too, I'll talk about it in a minute, and a battery. Now, to maximize the power transfer, we do what Tesla did. We tune the two circuits. We tune the primary, the transmitting antenna, we tune the receiving antenna. And when you do that, you have to take into account that the two antennas are coupled by a mutual inductance defined here. And this mutual inductance is a function of the coupling coefficient. And the coupling coefficient is sensitive to the distance. The larger the distance, the smaller the coupling coefficient. So you don't have a fixed system here. It is changing because you don't know exactly what will be the position of the receiving and transmitting antennas. Now, if you tune the primary and secondary, then the reactive element disappear, inductor and capacitor, and you are left with the parasitic resistance, secondary, parasitic resistance the primary. At the secondary, you have a current source due to the mutual inductance. Again, here we have a coupling coefficient, which is a function of the distance. And as it turns out, you have a sort of virtual resistance, which is reflected to the primary, which has also dependent on the mutual inductance and the actual resistance that you have in the circuit. Now, if I represent the system as a transformer, which is another way of looking at it, actually it's a transformer. And this transformer has a magnetization, you might say, inductance and leakages. Now, these leakages are a function of K, the coupling coefficient. So they are changing, okay? They are not fixed, like in a transformer, which is built in a fixed structure. So if you look at it this way, you come to realize that rather than having one resonant, this is a so-called multi-resonant network. Because, for example, if I replace this whole thing by Thevenin, I have a equivalent source plus an inductance or impedance that looks like this, and then you have another resonant here. So there are many resonances here, not just the one that is classically used. And here is an example. I can, by changing this capacitor, I can reach two resonants. Each of them could have a high efficiency and high power. Okay? So the point that I'm making is that you can now run a wireless power transfer with a variable capacitor to pick up these resonances. And also, even if you are working with the regular resonance, notice that you have to be tuned all the time. Now, if you have two circuits, they are warming up, the values of the capacitors are changing, so you lose the tuning. So if you have now an extra, way to tune the circuit, another parameter, an extra parameter, then you can optimize the circuit more than you have it today. So this was the objective of this particular work that has been published, by the way. So here is a simulation of what can be done. This is now changing the capacitance, and these are the peak outputs that you get. And here is a system that was built. We have a transmitter, receiver, variable capacitor, and a bias. Again, we can use one variable capacitor with a DC blocking or two variable capacitors. And here is another point that I like to explain, which could be very, very useful to whoever wants to use this technology. As I've said, it's public domain. Now, obviously, in some cases, you may wish to have a larger capacitance change that you can get from a given capacitor. Suppose you have a capacitor, but you want a much larger capacitance change. What can be done is to combine this idea of a voltage-dependent capacitor with a bank of a switched capacitors. Now, the bank of a switched capacitor, this is something that was done earlier. There are some papers that people have used it. Now, what's the downside here is that the resolution depends on the number of capacitors. If you want good resolution, you need many, many capacitors. By the way, the best way to do it, of course, is to choose the values in a binary way, like a binary number, and you select the capacitors so as to get all the steps, all the bits, you might say, from 0 to the maximum value. So the downside of this thing, which is very simple and very nice, is that you don't have good resolution unless you use many, many capacitors. On the other hand, if we combine these two ideas, we add in parallel a variable capacitor, just, you might say, for the last bit of the number, then I can close the gap. And I can get any number with infinite resolution of the capacitance. So this is very powerful, and we've used it a lot already. And this could be very nice because you get any number you want. You are not restricted. You just need a little bit of a change, and then you can get everything. And these are very easy to implement. These are just MOSFETs, which are driven by a microcontroller, which you anyhow have in the circuit, so there's no problem there. So here's the experiment we did. This is a project is for a submarine. unmanned submarine, not for war. And this is an area that is now expanding a lot for unmanned submarine for many things: environmental, cleaning, observations, inspection, many things. And obviously, a submarine has unmanned submarine has an electric motor and batteries that you have to charge. Now, to charge a submarine, it's a bit tricky because there's water. You have to worry about shorts, etc., connectors, underwater connectors. That's very difficult. So therefore, wireless power transfer is ideal for this case. So it's more than convenient. It's important. It's really added value. So here are mock-ups of a little submarine here, and this is the charging station. Okay, and these are the two antennas for the receiver and transmitter. And this is the system that has been built. You see that we have the transmitter, we have a rectifier, and the resonant circuit here. Here is the capacitor bank. We use 3 capacitors. Actually, we could get by with 2 capacitors. We had enough of a change with this. And this is the driver, the micro, and then we measure the current, and we have a sort of a algorithm that looks for the maximum point, might say maximum power point, so that you have maximum charging of the battery. Now, this is a mock-up, so the currents are really low. It's just a demo unit. And what we see here is the capacitance change that was required for this experiment, okay? And here are the optimization or the tracking. This is capacitance. This is for 2 different distances, which are translated into coupling coefficient, the 2 coupling coefficient. And here we see that by changing the capacitance, we get maximum current of charging, and here also maximum. This is, of course, higher because the coupling coefficient is larger. So the larger coupling coefficient allows you to get more current. Now, the difference between these two is the simulation and measured value, and the difference is explained by the fact that we have not accounted for all the losses in the circuit, parasitic resistances and things like that. So there's a distance, but the peak value are the same thing. So it looks that we can actually have a good simulation by trimming of the actual operation of the circuit. Okay, this is then the planned set of slides. I have one more thing I'll show you because we have the time. I didn't think we'll finish in time, so I put it in May. Let me just say that I do believe that this technology of using a controlled capacitor is very viable, and that eventually many applications will show up in this area. Another wireless, this is a set of references. Some are our papers, and some are relevant papers that I found. There are, of course, many papers relevant to this on voltage-dependent capacitor, etc. You find in IEEE Explore very easily. Now, another study that we are going to present, there's a conference in London in June, and it is, again, wireless power transfer, but from another angle. Let me go back for a second here. We have the time, so I'll explain it here. When we work in the resonant situation, in which the transmitting antenna and receiving antenna are tuned to the switching frequency, we end up with this equivalent circuit. Now, you see here a term which is kind of interesting. This is the reflected load to the primary. This is using a classical textbook mutual inductance model of two inductors. Notice that we have these parameters, which mean that this is our AC, and here we have a omega, the switching frequency, mutual inductance. Now, in order to get high power, you want this resistor to be as small as you can, because this is the excitation you have. So the smaller resistor will give you a high power, but efficiency will be lower because we have a resistance of the system, of the wire, of the transmitting antenna. As we know from basic electrical engineering, maximum power is obtained when these two are equal. But then the efficiency is only 50%. So there's a trade-off. You can get high voltage here, but low power and high efficiency, or you can get high efficiency with low power. Here comes this notion of impedance matching. That is, in many systems today, people are actually introducing here a DC to DC converter to change the impedance of the load so that when reflected to the primary will give you the optimum result in terms of power and efficiency. Okay? Another way to do the impedance matching is by regular impedance matching network, and one of them is capacitor-based matching. That is, to have two capacitors which are used as an impedance matching between this circuit and the load. This network is changing the impedance that you see here. Now, you can do the same thing within a converter, a buck converter, but then, of course, you need the switcher, etc. There's power loss associated. If you use these two capacitors, you may need to change this ratio of capacitors to optimize it. So here comes the idea of using, for the matching, a variable capacitor. So by changing this capacitance, you can match it better to the load and get higher efficiency, or the efficiency that you wish. So here are some experimental results here, which are showing how you can match the actual resistance and get a apparent resistance which is different, and thereby change the ratio of the power and efficiency. So this is another way or another possible application. I think, gentlemen, this is just about what I had here. If there are any questions, I'll be more than happy to answer if I know the answer. And if there are any comments or idea or suggestion, I'll be more than happy to hear.